Let's analyze the one example of output noise calculation. Common source amplifier cases of CMOS using R and NMOS. This is both power, VDD and VS ground, and this is N channel gate drain source. This is input and this is output. As run by page 239, after some pages, after proceeding some pages, with proceeding some pages, we know amplifiers having input, ground line, two-port representation of amplifier's input and output. We need voltage noise and current noise. To calculate the output noise or output current. And we say V out to Vn1 noise 1 of out, V sub noise 1 of out squared bar is appeared in on the output of the amplifier two-port system when this is open, this current flowing, only this current flowing. This is short. When it's short, the current is looping the noise sources. Voltage is just voltages appear. Noise voltage, only noise voltage. In noise voltage, only noise voltage is must to be considered in input shorted cases. This volt noise is amplified and appears in output. So we say V sub N1 out squared bar. And N2, Vn2, if this is converted, use current, which is not shown on page 239. Of course, input shortage cases can generate I sub N1 out squared bar, considering current noise. On the other hand, if input is open, only direction is okay. In input square bar is contribute for the noise generated for output, which is said V sub N2 of out square bar, or I sub N2 of output squared bar. Input short cases, two cases. We use two cases. Input short or output short. Input input open. When input short, we can get Vn1 out or In1 out squared bar, or when input open, we can get Vn2 out squared or In2 out squared. Suffix 1 is for input shorted cases, and suffix 2 is input opened cases. We use these models separately. And of course, these values must be the same. But why we understand, maybe because of this text, why we use both of these noise and current sources in input, because we need to know those both both contributions of noises for output noise. Then we can concentrate on input noise in short cases, input current power in open cases, separately generate different expression of output in these. This is a general case, and this is limiting case, or by this book, extreme. So two extreme cases, extreme cases. Considering two extreme cases is very useful to generate, use easier extreme case to derive expression of output noise voltage power or current power, or utilize both of them and equalize these terms. We can get something what we want. Using both combination is the assumptions, using these into the formula, we can generate the proof of the assumption extreme cases is right, or the consistency of the extreme case modeling, and why we can use these extreme cases is reasoned by general cases consideration proof, something kind of just a little bit tedious transformation of the formula is needed, but not so difficult. In a sense, easily supported by general cases. We can use two extreme cases models for getting output noise or current powers as a power. So in this common source cases, what is output voltage noise? And this is GM, this has GM M1. NMOS M1 has the size giving GM conductance, cross conductance value of GM we don't know input impedance is open, and we have no voltage noise there, and we have noise current there, maybe, but in this most devices cases, we don't have any leak noise or voltage to actual ideal device. It is not connected anything, so we only have output current noise, modeled by like this: the I n out squared bar, and also so this is 4kT gamma GM output channel noise current, and this amplifier has a DC gain of GM RD. This is RD. When this is RD, GM RD is this amplifier's volt DC gain, and way out. Output noise. If this has noise voltage of 4kTR of Vn squared Vnd, and so this node is modulated by this current noise, so this voltage has Vn out square is 4kT gamma GM R squared is appears by this current. This has no current, but this has 4kTR thermal noise voltage. The thermal noise voltage and this modulation is non-correlated, so must be added 4kTR. Really? Thinking like this, we can get this and express. But we ignore the explanation and the description and consideration for 1 over f noise here. 1 over f noise is a flicker noise, in other words, is generated in the gate oxides because of the displacement in the gate oxide, capturing the electron from channel and releasing sometimes, which is said random telegraphic motion signal, random telegraphic signal. So this is, in other words, RTS, random telegraphic signal. It appears in the input. So and modeled by input noise. voltage, power, which is reversely proportional to F and WL and Cox WL and constant K over Cox F LW, and inversely proportional Cox LW F, usually written after this, like this, K over Cox LW F. This is neglected. This frequentoid or RTS neglected. Neglected. And this is 4KT. RD. This is GMRD. OKT gamma Nanjara contrast times GMRD squared. Something input deferred noise times the amplifier for DC gain per squared is the output one. So this is, if it transfers like this case, this pattern, we can get input deferred noise. So GMR, this is G divided by GM, and this is divided by 4KT R GM square RD, GM squared RD squared RD. Or this is output resistance. What is out? The voltage of noise equals current noise of output squared times output resistance RD squared. So to separate RD squared, we can get GM squared is there, GM squared, the GM gamma GM plus OKT over RD. So we've already learned the expression of current noise of register compared by 4KTR, voltage, power, noise. Like this, the current noise of R equals 4KT over RD. So we know this, and we know this, RD, and output register, output current and output register are linear time invariant systems. Like we can use this like this expression, and I square RD square is this, and so current and RD is this. So non-correlated voltage noise is RD, and the same expression. There's no contradiction. Very consistent. And on the other hand, we can separate GMRD squared. We get input referred noise of this amp. Input referred Vn in squared bar equal 4kt gamma over gm plus 4kt over gm square rd. Of course, neglecting this flicker noise. If we consider this flicker noise, input referred noise must be added by this k over c oxl wf. Okay. What we did is on the 4-step procedure. First one is find each component's current voltage noise, current noise, voltage, current voltage noise, current noise to transferring voltage noise, and find the transfer function of this amplifier GMRD, and adapt all the components and adding GMR, multiplying GMR, getting V out. Following just like this method is not the following, but procedure following the procedure of this textbook 4-step procedure, we must find current. Input referred current noise of this channel. Input referred. Because GM V in equals I out. I out squared is this, and GM squared V in squared. Transconductance. If I out squared divided by transconductance squared is input noise voltage squared. So this divided by GM squared is this. This is input referred NMOS channel noise, and the input referred register channel noise is GM squared 4kt over RD divided by GM squared. This is add up because it's not non-correlated, and multiplied by transfer function GMRD squared, giving Vn out squared bar. It's easy to find, but not so easy, not so easily found. 4kt over GM square RD in a short sight. And what we have voltage node 4ktr, voltage node 4ktr divided by GMR squared. Is GMR squared this is this, but it's vice versa. It tautological. So in this case, it's easy to find voltage noise adapt to output voltage noise, and using this transfer function, of course, in this 4-step, this is 3 steps of this, 4 step, step 4, and we can get inversely input referred voltage noise. The step 4 procedure is not concrete fixed procedures. Mixing procedure is available or useful. We found that in this example. Let me see how to derive this without these. We couldn't get input referred voltage noise of the resistance, output resistance RD, considering DC voltage gain GMRD. Watching, please, looking at this circuit components and connections, topology, considering enough thinking. After that, we can use this. Well, because we remember this format easily derived, but in other cases, having very difficult, not so rules of thumb, easy guess derivation of the amplifier transfer function. We don't know this easier, more difficult. So in this case, written in page 237, input referred noise is discussed, and before that output noise discussed. Of course we assume lambda is 0, so lambda channel modulation constant, so RO or NMOS or P channel MOS goes going to infinity, so parallel resistance of channel is neglected, so RO in parallel RD is RD, so R out equal just RD. This is because of lambda equals 0. I must comment this lambda equals 0 in this model. And in this, we must identify the source of noise and find the transfer function to the output, multiply these spectra by the squared magnitude of the transfer function, and as a result, we model the thermal and flicker noise M1 by 2 current sources. We also represent the thermal noise by RD by a current source. Since these current sources are RD, it's transfer functions. Know that the noise mechanism added as power quantity because they are uncorrelated value given by this formula represents the noise power in hertz, the frequency f. The total output noise is obtained by integration. The textbook of second edition says using this approach to get output noise of this common source amp lambda equals 0 or M1. We know current, channel current, power, noise, and we know this resistance, current, power, noise, and we know the output impedance RD, when R equals lambda equals 0, and this is power, so RD squared is multiplied to give Bn out squared power. Well, this is not a transfer function, but well, this is in a sense transfer function of the amplifier. Output resistance times output current. So step 4, using voltage is difficult to find out, but using current is easy. Using current, we need to get RD. So the 4th step is not so powerful or completed. I've read about the lemma to get this approach, and I think you understand also the lemma, and you sometimes use this, but I systematically rearrange the formula method to get the method to derive the noise representation of the output or current, or and when is needed, respectively, current or voltage. This we must check the lemma here. This representation, this approach is lemma with 4-step procedure. Useful for this CS stage amplifier to get output noise power. Lemma, and I afterwards use this lemma. Transconductance of system Gn and giving output current I out equals Gm V in. This and and I out equal V out. R out is looking this into from the output when input shorted to the ground. Output resistance times R out gives I out times the output resistance gives V out. Also V out, V noise, we have noise about squared equal given by I noise about output squared about times R out squared. These two lemma uses many times, almost all the times, to easily calculate the output noise or output signal or representation of the signal transfer in many cases. So we remember this lemma, this format. In the CS amplifier tie example, use this lemma. And in out is already non-correlated components are already given from first side. On the first side, we can get these components. Expression is very easy. And our out is just RD. Lambda equals 0 in case lambda equals 0. And we get this. And input referred noise is after that, coming after that. But just I've already said and explained. I use 3 expressions to derive the output voltage noise and input referred noise in these cases, CS cases. But systematically, before that I said two extreme cases used and useful. So the textbook explanation is somehow not so clear where we use that 2 cases. So consistently I use to get V out 1 or 2. Sorry. We try just try to wait a minute.